So for this next problem, we're going to look at problem 3.33. And it's a little confusing because we haven't seen this one in the homework yet. But what we are basically given is the weight of these blocks. We're told that this weighs 6 pounds. And I'm getting that same, it's embarrassing because this has happened to me many times over the last few days. This has a 6 pound weight. And if you're wondering, why don't you just go to the supply cabinet and get more pens? What happens this time of night is no one else is here. And the admin locks the supply cabinet before she leaves, and she keeps the key hidden. So I actually don't know where that's at. So we have the weights of each of these blocks. And what we're interested in finding, you can assume that like when this was attached originally, that this point of connection was somewhere up by the ceiling, and it's kind of going to drop, and it's eventually going to get into equilibrium where basically the pull of, based upon the pulley system, the pull of these two actually going down is going to be counterbalanced by the pull of this in the middle going down. And that sounded confusing what I just said there, but when we actually draw the free body diagram, we'll be able to see it. So what makes this problem a little bit confusing is usually when you draw free body diagrams, you're looking for a force and you try to pick a point in the body that you can kind of separate from its surroundings and actually have the force that you're trying to solve for included in the free body diagram. But what we're going to find here is it's not a force that we're actually trying to solve for in a free body diagram. It's a magnitude of a force. It's one of the geometrical parameters. So that's what makes this a little bit different. So if you didn't know how to start this problem, you probably just assume this looks like a lot of problems we solved before where we've actually drawn a free body diagram on the point of connection between multiple cables. So let's just actually start by doing that, and we'll show why that is actually the correct approach to use here in a minute. So I'm going to just segment this portion of the body from its surroundings. That's point A there. And the question is how, when I remove everything else, like I remove this portion of the rope and the block hanging below, and I remove this entire portion of the rope passing over the pulley and the 6 pound block, and the same thing over here, how should I replace their effect? Well, clearly, if you think about it, when you cut that 8.5 pound force out, you have to replace its effect by pulling that portion of the rope that's left on that point of connector, pulling it 8.5 pounds down. And that's an example that we've looked at quite a bit up until now, why that works. Now, you might be a little bit confused when you actually cut this entire portion of the weight out, how you would replace its effect in terms of how it acts on the point of connection A. So remember, and I kind of pulled up the slide because someone I'm sure would say, oh, we never went over that, but I wanted to make sure that you saw that we did. When you have a rope passing along a pulley, note that the tension in that cable is actually constant throughout the cable, even when it passes along the pulley, as long as you're assuming it's an ideal pulley. I don't think in this class we actually touched anything that's not an ideal pulley. But what does that mean? Well, that means if clearly, like if you have a 6 pound crate, in this case, connected to that rope, there's 6 pounds of tension in the rope. So when it passes over the cable, it's kind of like that this portion of the cable is still pulling by 6 pounds in the direction that's defined by this angle that really is related to this 4-foot horizontal displacement and this S feet, which is what we're trying to solve for, vertical displacement. So hopefully that kind of justified to you that the effect of what's going on with this cable and pulley system is actually pulling this up by 6 pounds because we have the 6 pound weight going over the pulley, and that the pulley system is going to translate and actually redirect that force acting on this point of connection in that direction. And that same thing is going to be true. You can kind of argue it to yourself for when we replace the effect of everything that we've removed over here in the free body diagram. So everything over here is just tending to pull this point of connection up by 6 pounds, pull the point of connection up by 6 pounds, pull it down by 8.5 pounds. So we know that if this system is in equilibrium, the system must have sagged enough such that the resulting geometry actually makes this all true. And that's what we don't know. So usually when we don't know the geometry of something, and I'm kind of just going to draw in some coordinate axes here, you start by just labeling some angle theta. And you might ask yourself, well, what is theta? Well, it's the separation, the angular separation between the horizontal and the line of action of this force. Well, since this is a tension, we know that the line of action is just along the cable. So theta is exactly that. So theta in this actual triangle, like you can express it in terms of S. Hopefully everyone sees this. It's a triangle where this side length is 4 and that side length is S. So I'm just going to, for now, I'll just say it's a function of S. If we know theta, we're going to be able to get S for the geometry that we have. So I'm just going to assume that there's some way I can find theta, and I'm going to decompose both of these forces. Hopefully everyone would agree by now that this force is going to have a positive X and a positive Y component. So it decomposes into 6 cos theta, 6 sine theta. And this force, since this is also theta, and hopefully everyone sees that, same dimension here, 4 feet, same sag here, S, excuse me, it's going to be the same other than the fact that its x component is pointing to the left. So it's going to be minus 6 cos theta and then 6 sine theta. Okay. So if I were to enforce equilibrium on here, remember, since this is a coplanar force system, you're going to have two equilibrium equations. One says that the sum of all forces in the x direction must be 0. Well, this doesn't have a component in the x direction. So what that means is that the pull of this rope to the right, which is 6 cos theta, minus the pull of this rope to the left, remember that when you add vectors, you just take the sign with them, must be 0. And this is just a bunch of fancy math to say that 6 cos theta is 6 cos theta, and that's always true for all theta. This is what's known as an actual identity. So we're not going to get any useful information from there that's actually going to allow us to solve for theta. This just says for any theta, this must be true. Regardless of how far it's sagged, the pull to the right must equal the pull to the left. So let's actually try to enforce our other equilibrium equation, which is that the sum of all forces in the y direction must be 0. Well, what would that give us? Well, pulling up, we have the y component of this, which is 6 sine theta. That's actually identical to the y component of the other tension, 6 sine theta. And that's counterbalancing the weight, which is pulling down, of block E, 8.5 pounds. So if we set that equal to 0, now we're getting somewhere. Because what we find is that 12 sine theta must equal 8.5. And I don't know why I put the unit in there. It's all in pounds. What that means is that sine theta must equal 8.5 divided by 12. And what that means is that theta is just going to be the inverse sine of 8.5 divided by 12, which if I actually compute that, is going to be, you can see we have the answer there. It's going to be 45.0995 degrees. And I'm going to carry all the precision around like we usually do, just to make sure we don't run into any rounding errors. Okay. So the question wasn't, though, so what this is really telling you is this is how much sag you need measured in terms of the angle in order to give you equilibrium. But the question wasn't what angle does this actual point of connection sag to. It's actually how much physical distance of sag do you get. Well, if you think about how could you relate the angle theta, now that we know it, to the unknown s and the geometrical information that we're given, which is 4. Well, if you look at that, that's just opposite over adjacent. So what that means is that the tangent of theta, and we know that theta has to be 45.0995 degrees, must be equal to the opposite side length, which is s, divided by 4, which is the adjacent side length. So that means that I can actually solve for s by just taking 4 times the tangent of that angle that I just computed. And if I go through and do that, I will get 4.0139, and that is going to be in the length units of the problem, which is in feet, and rounded to 3 significant figures, that would just be 4.01 feet. So it might have looked like a little bit of a different problem, but it's really not that different at all. You still just need to enforce equilibrium on a particular point in your body. Ideally, since we're only to chapter 3, that will lead a concurrent force system. That way you can do the statics of particles. And ideally, that free body diagram should somehow involve the parameter that you're trying to solve for. Typically, up until now, that's been a magnitude of a force. What made this problem a little bit different is it was actually something related to the direction of the force. So in this case, we just assumed that we could solve for the direction of those ropes, which we defined by theta, and then we use that eventually to find how much sag was actually induced in that system.